Good afternoon, everyone. It's my pleasure to present our recent work here. First, I would like to acknowledge my co-author, Dr. Chen, who actually did most of the modeling work here, and the support from Los Alamos National Laboratories LD-RD program. So basically, the production of shale gas in a well declines rapidly. These are production curves for representative wells for different formations. We can see these curves follow an exponential decline for the first 2 years, followed by a long tail that can last maybe over 10 to 20 years or more. The fundamental science and mechanisms driving this decline are poorly understood. So, but it is assumed that the mechanisms behind the production curve include initial flush of gas from fracture network and the transport of gas from small fractures and transport of gas, free gas in shale fracture to shale matrix to fractures, and desorption and transfer of actually gas absorbed to corrosion. Obviously, these processes occur at different lengths and time scales. Although the initial fast production is attributed to the initial flush of gas from fracture network, the long-term production is controlled by smaller scale phenomena. Specifically, the cumulative production over decades is controlled by how fast the gas in the shale matrix or organic matters transfers to fractures and ultimately to the fracture network. So obviously, a slight or moderate improvement of gas mobility in small pores may lead to a significant increase in cumulative gas productivity over years. However, this requires a fundamental understanding of gas transport in nanopores. So actually, as the previous speaker pointed out, so the different gas flow regimes can be characterized by the Knudsen number ratio between mean free path of gas molecules to the characteristic length. When the Knudsen number is small, the continuum assumption of fluids is valid, then the Levi-Stokes equation or the Stokes equation can be used to describe gas flow at the pore scale. And the upscaling or value averaging of the Levi-Stokes equation gives rise to the Darcy equation, which can be used to describe the gas flow at the continuum scale. So for the small length scale of the nanopores leads to a very relatively large Knudsen number. That means the Stokes equation or Levi-Stokes equation is no longer valid to describe gas flow at the pore scale, and consequently, the Darcy equation needs to be modified. So, in fact, Klinkenberg conducted experiments for gas sleep actually back more than 70 years ago, and proposed a first order correlation for the apparent permeability, where the Ki is well, actually this is the apparent permeability, which actually is a permeability measured using gas, and this is a intrinsic permeability, which can be which is a permeability measured using water. So the ratio between them is called the correction factor, where the B is the Klinkenberg coefficient, which is used to account for slip effect. And later on, these researchers propose second-order correlation for apparent permeability. Numerically, there are actually very sophisticated numerical models developed to solve gas flow with slip effect for simple geometries. However, these models are very hard to extend to complex nanogeometries. So alternatively, the apparent permeability can be calculated based on this dusty gas model. According to this model, the total flux in a nanopore can be calculated based on, can be considered as a combined result of viscous flow and Lucent diffusion. So the apparent permeability can be written in this way. Then one can just solve the pore-scale fluid flow equation to derive the intrinsic permeability based on the Darcy equation. And then one can solve the pore-scale diffusion equation to get the effective Lucent diffusion. And then based on this, one can calculate the apparent permeability and then the correction factor. So actually there is the analytic solution for the dusty gas model for a gas flow in a tube. And this figure, in this figure, this analytic solution is compared with different empirical correlations. We can say it's in good agreement with second order correlation. And for complex geometries, certainly there will be no analytic solution for flow field or concentration field. So one has to resort to numerical models. So, and the solution for, here we use the Lattice Boltzmann method because of its advantage in handling complex geometry and physical chemical transport processes at the pore scale. And the solution to both flow and diffusion equations is straightforward, except that here the diffusivity is related to the local effective local pore diameter. Here we use the 13. This diameter is actually varies spatially. Here we use the 13 direction average method to calculate this effective local pore diameter. So this pore load is located at the center of the cube. By connecting this point with the center of the 6 faces, 12 edges, and the 8 corners, one can actually get 13 directions. By averaging the pore distance in the certain direction, we can get the effective local pore diameter. Then use this in the diffusion coefficient. So we see some simulation examples. This is a SEM image of Shale with a resolution of 2.8 nanometer. And this is a reconstructed 3D Shale structure using Markov chain Monte Carlo method. And we did some structural characterization of the constructed shale, including pore size distribution using the 13 direction averaging method, and as well as the connectivity. And we can see some pores are connected, others are not. So some of the dead portion of the void space is removed from our simulation. So using this geometry, we solve the Lattice Boltzmann equations for single phase flow with low slip boundary condition and diffusion equation, and to obtain the flow field, velocity field, and the concentration field. This figure shows the concentration distribution, and this shows the pressure and the streamlines. Based on this, we can calculate the correction factor. As a function of Lucent number and the pressure, we can see the value of the Lucent number is always, the value of the correction factor is always greater than 1. and can be as large as 100 at low pressure. This means that for gas flow in nanoporous media, the long continuum effect has to be considered, and the permeability used in the Darcy equation has to be modified. Oh, okay, time is running out. We also did some simulation of transport properties in reconstructed nanostructures of organic matters in shale. So nanostructure of organic matters in shale are very complex, and basically the pore space here is described by uniformly distributed spheres. So the pores of sphere shape are randomly placed in a domain, and the porosity, radius of spheres, probability for spheres to overlap, and overlap tolerance are specified and varied to investigate their effect. So this shows the 3D representation of a reconstructed corrosion structure, and this is the concentration field. And then we calculate this figure shows the the effective Knudsen diffusivity for the organic matter. So one thing we can say is they revised the Boltzmann equation. Actually, it overestimates the effective Knudsen diffusivity and underestimates the tortuosity of the nanoporous materials. And this figure shows the permeability, intrinsic permeability as a function of porosity. We can say the case equation is still a good approximation for the organic matter here. And based on this, we calculate the correction factor at various intrinsic permeability. We can say this correction factor increases as the intrinsic permeability decreases. So basically, here are some conclusions. So basically, we presented the first numerical study to calculate the effective Knudsen diffusivity and apparent permeability based on computationally generated shale and organic matter structures. And the tortuosity of the shale or organic matter is much higher than that commonly employed in the Boltzmann equation. And such high tortuosity leads to extremely low intrinsic permeability. So correction of the intrinsic permeability is performed based on the dusty gas model, and the correction factor over a range of Knudsen number and pressure is estimated and compared with empirical correlations in the literature. So for the widest pressure range investigated, the correction factor is always greater than 1, indicating that Knudsen diffusion always plays a role on shale gas transport mechanisms in the reconstructed shale or organic matters. Thank you for your attention.
While we're changing over speakers, we have time for one quick question and one quick answer. Yes, in the middle.
Several times you mentioned the high tortuosity. Could you give actual values? What sorts of tortuosity values do you see?
Okay. I don't have the value right in my mind, but if you're interested, I can find in a paper. Actually, this has been accepted for publish in scientific reports. And I can only tell you right now that's the indirect indication is that the let's say the coefficient used in the Boltzmann equation actually originally is 1.5, but here we found out that the coefficient could be 2.8 to 4 in this range. Then the results will be in better agreement with our numerical simulation. Thank you.
Thank you.
Thank you.
Okay.